Okay, so welcome everyone to today Mathematics of Motion seminar. Today we'll have Łukasz Cholewa, I hope I'm saying that right, who will talk about, yes, okay, on dynamics of expanding Lorenz maps. So Łukasz, take it away.
Thank you, and thank you very much for inviting me. So the talk will be based on joint works with Piotr Oprocha, paper on alpha limit sets in Lorenz maps and preprint renormalization in Lorenz maps, completely invariant sets and periodic orbits. The plan of presentation is as follows. At first, I will give you a definition of the main object, that is a Lorenz map, and say a few words about motivation, why people study these maps. Then I will provide some basic background from topological dynamics. And okay, because any expanding Lorenz map has discontinuity, it does not forms a topological dynamical system. So we use something which is called standard doubling points construction to view expanding Lorenz map as a continuous map on Cantor space. So I will describe this procedure. Then I will say something about symbolic dynamics and kneading theory for Lorenz maps. Kneading theory allows us to present every trajectory of Lorenz map as a binary sequence. Okay, and using provided tools, I will show you how we may use it to study alpha limit sets in Lorenz maps. Alpha limit sets are alpha limit set is a dual concept to omega limit set, and it was believed that alpha limit sets in Lorenz maps are completely invariant, that is forward and backward invariant. But it turns out that it's not true in general. So I will construct appropriate Cantor example of expanding Lorenz map with alpha limit set that is not completely invariant. And I will also discuss our recent progress in study of alpha limit sets in Lorenz maps. Okay, so expanding Lorenz maps are interval maps with a single discontinuity. This discontinuity is called a critical point, and these maps are continuous and strictly increasing on both intervals 0C and C1, where C is a critical point. Moreover, there exists one-sided limits at critical point C equal to 1 and 0. And the last condition is the reason why we call these maps expanding. It says that f is differentiable with slope greater than 1 everywhere except at most a finite set. Observe that the last condition implies that the set of all pre-images of critical point is dense in interval 0, 1. The density of this set is very important for us. And the second thing, we always assume that the image of critical point C is 0 or 1. Okay, a few words about motivation. So these maps appear as a Poincaré maps in geometric models of Lorenz attractor. Here we have some fundamental papers on this topic. So very briefly, the idea is as follows. in order to understand the dynamics on Lorenz attractor, people started to study simpler models like this one here. So here we have some flow, and if we take an appropriate Poincaré section, then it should define the Lorenz map as a first return map to this section PQ. Okay, but these maps are also important, for example, in number theory, in particular in study of expansions of real numbers in non-integer basis. Here we have two pioneering articles on this topic. And in addition, there are also some applications in fractal geometry. They have some applications in fractal geometry. Okay, so some basic notions from topological dynamics. So let X be a non-empty set, and we have map T on X, defined on X. For any n, by T to the n, we mean a composition of the map T with itself n times, and T to 0 is an identity. Okay, an orbit or trajectory of point X under the map T is this set, so the set of all iterations of the point X. Point X is periodic if there is some natural number n such that f to the n of x is equal to x, and if this number is the smallest natural numbers with this property, we say that the point X is n-periodic. Okay, and one periodic point is called fixed point. And a non-empty set is completely invariant if it is equal to its image and its pre-image. Okay, if the space X is compact and metric and the map T is continuous, then the pair XT forms a topological dynamical system. Okay, and if I have two dynamical systems, XT and YS, then if there exists a homomorphism H from X to Y such that this condition holds for every X, then we say that dynamical systems XT and YS are topologically conjugated. And in this case, the map H is called topological conjugacy. Okay, and note that topologically conjugated dynamical systems have the same dynamical properties. So these systems are equivalent. Okay, so because, as I said, any Lorenz map has discontinuity, it does not form a dynamical system, but we can perform a so-called standard doubling points construction to obtain a continuous map on a Cantor set which is closely related to our expanding Lorenz map. This procedure is described in the paper of Peter Wright for a more general family of maps. We adapted this procedure in our case of Lorenz map. So I will describe it now. So at first, consider the set of all pre-images of critical point C. except possibly 0 and 1, okay? This set C, capital C, is dense and countable. So this is dense and countable set. And I take any point from this set and split it into 2 points. So I take, for example, the point E and split it into 2 points, E minus and E plus. And I have the hole between these 2 points, okay? And I do it with any point from the set capital C. What is important, I do not modify the other points. Okay, this way we obtain a new space X, and because the set C is dense, in this new space, I will have between any 2 different points, I will have some hole. And reversing this procedure, we obtained a map pi. This map glues back together inserted points. So, for example, P of E minus is equal to P of E plus, and is equal to pi of E minus is equal to pi of E plus, and is equal to the point E. This map pi is sometimes called a projection, and it is continuous map. Okay, so now I want to define linear order on this new space X. So take 2 points from this space X, and if points X and Y are the endpoints of the same hole, then we define the order in this way. So X is less than Y if and only if X is left endpoint of this hole and Y is right endpoint of this hole. Otherwise, X is less than Y if and only if pi of X is less than pi of Y. Okay, and this order is linear. So in particular, we can define open intervals and order topology on space X. Now I want to introduce a metric on space X. So, okay, so the formula for metric is quite complicated, but I don't want to discuss it in detail. I only will give you an intuition. So the intuition is that the biggest hole corresponds to critical point C, okay? So the hole inserted in the place of point C is the bigger one. And the more iteration it takes to hit the critical point C, the smaller the hole is, okay? And the second thing, the distance between 2 points, X and Y, depends only on the biggest hole between these points and the distance between their projections, pi of X, pi of Y. Okay, so it is a intuition how this metric works. What is important, topology generated by this metric and the ordered topology on X are the same. And with this metric, X is a Cantor set. Okay, and now I will define map F hat on this new space X, and I will do it as follows. At first, fix any point x which is not in the set capital C. So it is not a pre-image of the critical point C. Okay, and the image of this point x, let me a second. Oh, okay. So yeah. So I take point which is not in the set capital C, and its image is also not in the set capital C. In this case, the point, I did not modify the point x. So there is a unique point x hat, which corresponds to this point x, and the unique point y hat, which corresponds to image of point x. And in this case, we define simply that f hat of x hat is equal to y hat. Okay. Now let IE be an inserted hole in the place of point E, which is not a critical point. So it is some pre-image of critical point, but it's not a critical point C. Then we send its endpoints into respective endpoints of the hole inserted in the place of the image of point E. Okay, so I have the hole inserted in the place of point E, and I have the hole inserted in the place of point F of E. And then my map F hat sends E minus, so the left endpoint of this hole, to the left endpoint of this hole, and the right endpoint of this hole to the right endpoint of this hole. Okay. Since we did not modify endpoints 0 and 1, there is a unique point 0 hat which corresponds to point 0, and a unique point 1 hat which corresponds to point 1. And we define the image of point C minus to be point 1 hat, and the image of point C plus to be a point 0 hat. Okay, so C minus goes to 1 hat, C plus goes to 0 hat. And there is a last case. If the image of 0 is belongs to the set of all to the set capital C, so f of 0 is a pre-image of critical point, then we define the image of 0 hat to be right endpoint of the hole inserted in the place of f of 0. Okay, so in this case, f of 0 belongs to the set capital C, so I have some hole which corresponds to this point, and in this case, the point 0 hat goes here, and similarly in the case of the image of point 1. Okay, so this is the definition of map F hat, and what is important? For any point from space X, which is not C minus and C plus, we have the following condition. Okay, so in fact, every trajectory in space 0, 1 has a corresponding trajectory in the space X. more precisely, if I take any point P from interval 0, 1, then if P is not a pre-image of critical point, then the trajectory of this point corresponds to the trajectory of unique point P hat in space X. If my point P is a pre-image of critical point C, but it's not 0 and 1, then if image of critical point C is 0, then the trajectory of point P corresponds to the trajectory of right endpoint of the hole inserted in the place of point P. And similarly, if the image of critical point C is 1, then the trajectory of point P corresponds to the trajectory of left endpoint of hole corresponding to the point P. Okay, so the only exception when I don't have the corresponding trajectory in the space X is in the case when trajectory of point 0 contains critical point C and the image of critical point C is 1, okay? Because in the space X, the point 0 hat cannot hit the point 1. But in the space 0, 1, in this case, it may happen. So I iterate 0, it hits critical point C, and then it goes to 1. Okay, and the symmetric case, if I iterate the point 1, it hit a critical point C, and it goes to 0. It cannot happen in space X. In space X, if I iterate the point 1 hat, I can only hit the point C minus. So in this case, I have a periodic orbit in space X. Okay, so this essentially this space X and the map F hat, and the whole information about dynamics of my Lorenz map F is described by this map F hat. Okay, essentially almost every trajectory has a corresponding trajectory in space X. So okay, another thing is that since we defined the image of critical point to be 0 or 1, the image of map F is always 0, 1 without 1 or 0, 1 without 0, with only possible exception when F has a fixed point at 0 or 1. Okay, but this new map F hat is always onto. Moreover, this map F hat is continuous, so the pair X F hat forms a dynamical system. So we can apply standard definition from topological dynamics to the map F hat. So we can use the whole theory of topological dynamics to this map and then try to say something about corresponding Lorenz map. It is convenient to work with this map F hat and then try to conclude something about original Lorenz map. Okay. Moreover, the dynamical system X F hat is topologically conjugated to a certain subshift. I will discuss this fact in a moment. So we can study Lorenz map symbolically. The dynamics of map F hat is closely related to dynamics of the original Lorenz map F. So, for example, if I have some set E which does not contain points 0, 1, and critical point C, then this set is completely invariant under the map F if and only if its counterpart in space X is completely invariant under the map F hat. Okay, so now I will say something about symbolic dynamics. So denote by A the set of points 0 and 1, so it is our alphabet, and let sigma 2 be the set of all binary sequences. Any element of the set A to the n is called a word of length n. So for any two words of length n and m, I can define their concatenations as a word of length n plus m. And moreover, by omega to infinity, we mean the infinite concatenation of word omega with itself. Okay, we say that some word omega occurs in a sequence X if there is some number J such that this equality holds. So otherwise we say that omega does not occur in X. So for example, let X be a sequence 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. Then the words 1, 0, 1, 0, 0, 1, and so on occurs in X. But for example, words 1, 1, 1, 0, 1 does not occur in X. Okay, next we introduce the lexicographic order on sigma 2. So for any two sequences, we say that X is less than Y if and only if this condition is satisfied. So let's see it at the example. So I have two sequences, X and Y, and I look at the first position where these two sequences differ, and in this case it will be 1, 2, 3, 4, 5, 6, sixth position. So at this position X has a 0, Y has a 1, so X is lexicographically less than Y. And in the similar way, we can define the lexicographic order for any two words with the same length. Okay, we will consider the standard metric on sigma 2 defined by this formula. So again, look at the example. So I'm looking for the first position when these two sequences differ. And this is the position number 5. So the distance between these two sequences is equal to 2 to the power minus 5. Okay, so with this metric, the space sigma 2 is a compact metric space. And we define map, and the map sigma is the standard shift map. So I take some sequence and just cuts off it cuts off the first symbol. Okay. The shift map is continuous, so the pair sigma 2 sigma forms a dynamical system that we call full shift. And for any non-empty and closed set sigma, which is forward invariant, the dynamical system sigma and sigma restricted to capital sigma is called subshift. And we will consider two types of subshifts. Subshifts of finite type and lexicographic subshifts. So at first, what is subshift of finite type? So let F be some set of words, and we denote by sigma F the set of all sequences such that any word from the set F does not occur in the sequence X. Okay, and if this set is non-empty, then the pair sigma F, sigma restricted to sigma F, is a subshift. Okay, and the set F is called the set of forbidden words. Note that different sets of forbidden words may define the same subshift. Okay, so in particular, it may happen that one set of words is finite, the second one is infinite, and both define the same subshift, like in this example. Okay, but if there is a finite set of forbidden words which defines subshift sigma, then we say that this subshift is of finite type. Okay, so this subshift is of finite type if I can find a finite set of forbidden words which defines it. Okay, now a few words about lexicographic subshifts. So take two binary sequences, and denote the set sigma alpha beta as the set of all sequences that are always between alpha and beta. Okay, so I iterate the sequences and they are always between alpha and beta. And now assume that this set of sequences is non-empty, and the sigma alpha beta is the restriction to this set, restriction of the shift map to this set. Then this pair forms a subshift. And this subshift is called lexicographic subshift. And it turns out that any map f hat, which corresponds to some Lorenz map, is topologically conjugated to some lexicographic subshift. So lexicographic subshifts essentially describe dynamics of Lorenz maps. Okay, so now let F be an expanding Lorenz map with critical point C, and let F hat be map induced on the Cantor set X. Okay, and IC is a critical interval. So it's the interval inserted in the place of critical point C. Then for each point X, we define the kneading sequence as a binary sequence in this way that if the, it should be eta of X with index n. So here it should be n. Okay, so if the end iteration of the point X is greater or equal C+, then the end symbol of kneading sequence is 1. And if the end symbol of and if the end iteration of point X is less or equal to C minus, then the end symbol in this sequence is 0. And the kneading invariant of map F is the pair of kneading sequences of points C plus and C minus. Okay, a classical definition of kneading sequences does not use the map F hat. So you can define kneading sequences only using the Lorenz map F, but then you need to deal with one-sided limits. So this is the classical way to define the kneading sequence. I take point which is not pre-image of critical point C, and then I say the symbol of this sequence is 1 if the iteration of point X is greater than critical point C. And the symbol is 0 if the iteration is less than the critical point C. Okay, but if I want to define the kneading sequence for the point which is in the pre-image of critical point C, then I need to define upper and lower kneading sequence as these one-sided limits. And these one-sided limits are calculated through points Y, which are not pre-images of C. Okay. And then we define the kneading invariant of F to be the pair of kneading sequences of critical point C, the upper and lower kneading sequence of the critical point C. So you don't need to play with the map F hat, but instead of this, you need to work with one-sided limits, and sometimes it's not so convenient. But these two notions are more or less equivalent. So in particular, the kneading invariant defined in the way as I did it is the same as a classical kneading invariant. Okay. I will show you some simple example. So consider an expanding Lorenz map with a constant slope defined by this formula. Then the critical point C is 1/2. And observe that C plus always goes to 0 hat. 0 hat in this case goes to f hat of 0 hat, and then it goes to f hat of 1 hat, and it becomes a periodic orbit. And the same for C minus. C minus goes to 1 hat, then it goes to f of 1 hat, and then it goes to f hat of 0 hat. Okay, so in this case, the kneading invariant of this map will be 1, 0, 0, 1, 0, 1, 0, 1, and so on. And the second one is 0, 1, 1, 0, 1, 0, 1, and so on. Okay, so again, consider this map eta, that is our coding map, and observe that this map is continuous and strictly increasing. Moreover, the image of this map is compact subset of sigma 2. And for any point x, we have this condition satisfied. Okay, so in particular, the image of map eta is forward invariant under the shift map. So this map eta is a topological conjugacy between dynamical system x f hat and subshift eta of x and sigma restricted to this set. Okay, so as I said, we can study the dynamics of this map x f hat, so also the dynamics of original Lorenz map by studying a certain subshift. Okay, and probably the most important theorem in the kneading theory for expanding Lorenz maps comes from the paper of Hubbard and Sparrow, and it says that if I have expanding Lorenz map, then the kneading invariant of this map satisfies these two conditions. Conversely, given any two sequences that satisfy this condition, there exists an expanding Lorenz map with kneading invariant, which are these two sequences. And this map is unique up to conjugacy. So if I have two expanding Lorenz maps with the same kneading invariant, then the dynamics of these two maps are the same. Okay, these two maps are equivalent. Dynamics of these two maps are equivalent. Okay, so now the question is, what is the structure of the set of these all binary sequences that describes the dynamics of our Lorenz map? So let F be an expanding Lorenz map and F hat its extension to the Cantor set X. Recall that this dynamical system is topologically conjugated to the subshift given by this map eta. And then the set eta of x is in fact lexicographic subshift defined by kneading invariant of the map F. So it consists of all the sequences that are between these two sequences, sigma of eta plus, sigma of eta minus. So in fact, it is the set of all sequences that are between kneading sequence of 0 and kneading sequence of 1. So we have a we have the description of this set eta of x, but we can say more about it. So for example, we proved that if I have expanding Lorenz map F and F hat is its extension to the Cantor set X, then the following conditions are equivalent. So the point 0 is a fixed point, or critical point C belongs to its orbit, and the same for the point 1. It is equivalent to that the points 0 hat and 0, 1 are both periodic under the map F hat. It follows directly from the definition of map F hat. It is equivalent to that the kneading sequences eta plus, eta minus are both periodic under the shift map sigma. It is it follows from the definition of map eta, and the last one is not obvious. It is equivalent to that the this subshift is of finite type. Okay, so if I have periodic kneading sequences, then the corresponding subshift is of finite type. Okay, now we can move on to alpha limit sets in Lorenz maps. So recall that alpha limit set of point X under the map F is defined in this way. So it is the set of all accumulation points of all pre-images of point X. So in other words, a point Y belongs to alpha limit set of X if and only if there exists a strictly increasing sequence of natural numbers, a sequence of points from interval 0, 1, such that f to the kn of x n is equal to x, and this sequence converges to the point y. So intuitively, the alpha limit set of point x represent a source of the trajectory of the point x. As I said before, it was believed that the alpha limit sets in Lorenz maps, in expanding Lorenz maps, are completely invariant. But we found an example of expanding Lorenz map with alpha limit set that is not backward invariant. So it differs from its pre-image. And now I will show you the construction of this example. Okay, so the inspiration for our example comes from the paper of Glendening and Sparrow, and more precisely from this picture. Here we have some flow which defines a Lorenz map F. And okay, at first observe that the Lorenz map F, that is the first return map to this interval 0, 1, has two periodic orbits, GL and GR. Okay, so it goes somehow here to GL goes to GR, GR goes to GL. I have a two periodic orbit here. And we started to think what is the alpha limit set of this point GL, because we can observe that if we consider any left-sided neighborhood of point f of 0, so 0 goes here, so here I have the point f of 0, and if I consider any open interval p f of 0, after each iteration it grows, and at some point it must cover the point GL. Okay, so I take interval here, it somehow goes here, it goes here. So after each return to the interval 0, 1, this interval is bigger, and at some point it must cover the point GL. So the image of 0, f of the point f of 0, must belong to the alpha limit set of the point GL. But 0, the point 0 cannot belongs to this set. Okay, so this indicates that the alpha limit set of this point cannot be backward invariant. So now the question is how to construct expanding Lorenz map from this picture, okay, from this flow. So at first we need to find the kneading invariant of this map F. So look at the trajectory of the point C plus. C plus goes to 0 as always. Then it goes here. So it's again on the left side of the critical point C. Then it is again on the left side of critical point C. And then it becomes a periodic orbit. Okay, so 0 goes here, then it goes here, and here we have free periodic orbit because it goes here, it goes here, and it returns here. So the kneading sequence of the point C plus will be 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1. And similarly for the point C minus, we have a symmetric case for the point C minus. Okay, so we know the form of the kneading invariant of this map, but now the question is how to construct this map. At first observe that these sequences eta plus, eta minus satisfy inequalities from Hubbard-Sparrow theorem. So we know that there exists such an expanding Lorenz map. Okay, we can check these conditions and everything is fine. So for sure such a map exists. But how to construct it? Because the proof of Hubbard-Sparrow theorem does not lead to the exact formula for this map. F. So, for example, there is a paper of Bernsley, Steiner, and Vince, where they provide a characterization of kneading invariants corresponding to expanding Lorenz maps with constant slope. That is Lorenz map of this form. And in this case, for these maps, they also gave exact formulas for beta and alpha, defining this map with a given kneading invariant. So if I have kneading invariant, I can check if this kneading invariant corresponds to expanding Lorenz map with constant slope. And if yes, then I can compute beta and alpha. But unfortunately, this kneading invariant, these sequences eta plus, eta minus cannot be a kneading invariant of expanding Lorenz map with constant slope. So how to construct it? So our construction heavily uses the fact that these kneading sequences are eventually periodic, because then we can write down some equation which lead to the formula for this map F. You will see it at the moment. But okay, at first consider a map G of this form. We know that our map cannot have a constant slope, so we allow it to change the slope. And we consider map on interval -1, 1 for some technical reasons. When we construct it, we can rescale it to the interval 0, 1. It's not a problem. Okay, so we have a map G of this strange form, and we assume that parameters beta 1, beta 2, beta 3 all are greater than 1 to ensure that we have expanding map. And alpha 1, alpha 2 are some real numbers. Okay, so from the form of this map, we can observe that the one-sided limits at point P are equal and one-sided limit at point Q are equal. So the map G is continuous and strictly increasing on -1, 0. And because this map is symmetric with respect to point 0, G is also continuous and strictly increasing on 0, 1. Moreover, the left-sided limit at point 0 is equal to 1, and left-sided limit and the right-sided limit at 0 is equal to -1. To ensure the appropriate form of the kneading invariant, we will require additionally that G satisfy these conditions. So there are the conditions which describes how the trajectory of point -1 behave. So yeah. So observe that after 2 iterations, this map, this point become a periodic point. So this point is eventually periodic. Okay, and if these iterations belong to appropriate subintervals, then we will have appropriate form of kneading invariant. And these conditions, together with the form of map G, lead to the following equality. As I said, we heavily used the fact that the kneading invariants are eventually periodic in this case. It allows us to obtain this equality. And after simplification, we obtain this equation, which is satisfied for such parameters betas and alphas. Observe that indeed all betas are greater than 1, so indeed we have expanding map. And then we can compute the point P and the point Q, that are the points where the map changes the slope. And after that, we can rescale this map to interval 0, 1. So we have the map after rescaling is this one, the f of x. And this map is expanding Lorenz map with critical point 1/2. Here we have the graph of this map. As I said, it does not have a constant slope. It changes the slope, but at points very close to critical point and to endpoints 0 and 1. And now we can compute the trajectories of 0 and 1 and check that, okay, everything is fine. That means we have a form of kneading invariant as desired. Okay, and we can also find the two periodic orbit GL, GR. Okay, here we have the order of these points. Okay, so P1, P2, P3, P4 are the iterations of 0, and Q1, Q2, Q3, and Q4 are the iterations of 1. So we can check that indeed the kneading invariant of map F has this form. Okay, so what about the alpha limit set of the point GL? So consider this set W and this red set, union of these red intervals, and observe that that the image of this set is contained in W. So because 0 Q3 goes to P1 Q4, P1 Q4 goes to P2 Q4, P2 Q4 splits into two intervals. One goes to 0 Q3, the second one goes to P2, goes to P3 1. The interval P4 Q1 goes to P2 Q2, and the interval P3 1 goes to P4 Q1. Okay. And since this two periodic orbit is disjoint with the set W, and the set W is forward invariant, since that the set W cannot contain any pre-image of the point GL. So we can conclude that the alpha limit set of point GL is contained in the complement of the interior of set W. And in particular, 0 and 1 cannot belong to the alpha limit set of point GL. But the image of 0 and the image of 1 do belong to the alpha limit set of GL. We can consider any interval of this form xp1, like here, the blue one. And again, after each iteration, this interval grows. And at some point, it must contain the point GL. Okay. So, yeah, so indeed, the alpha limit set of the point GL is not backward invariant, because the pre-image of this set contains 0 and 1, but the alpha limit set does not contain these 2 points. Okay, in fact, we can prove that the alpha limit set of the point GL is a Cantor set, and it differs from its pre-image only by these 2 points, 0 and 1. But these 2 points make a huge difference, because if we consider the set of all pre-images of the alpha limit set of GL, then okay, so Ding claimed that this set should be equal to the alpha limit set of GL. But in fact, it contains a dense set of points not belonging to alpha limit set. Okay, so it is a huge difference. Yeah. And it is because if the pre-image of this alpha limit set contains 0 and 1, it also must contain the critical point. And the set of all pre-images of critical point are dense. So this is the reason. Okay, so now I will describe our progress in study of alpha limit sets in Lorenz maps. So at first, we proved with Piotr that if F is an expanding Lorenz map, and if I take some point x from the interval 0, 1, then the image of alpha limit set is always contained in this alpha limit set, and this alpha limit set is always contained in its pre-image. And indeed, alpha limit set may differ from its pre-image only by 2 points, 0 and 1. If alpha limit set contains a critical point, then it must be the whole interval. If the image of critical point is 0, then alpha limit set of 0 is the whole interval, and the alpha limit set of point 1 is empty or contain only 1.1. And the symmetric case if the image of critical point is 1. Okay, now let U be an open set, and by n of U we denote the smallest integer n such that the critical point C belongs to f to the n of this set U. Okay, so it is the first iteration when the set U covers the critical point C. Okay, and again, let F be an expanding Lorenz map and take some point P, which is not 0 and not 1. And suppose that the alpha limit set of this point is a proper subset of 0, 1. Then denote by E minus the point from the alpha limit set, which is the closest to the critical point from the left. And by L denote the first iteration when this interval covers the critical point C. And similarly, E plus is the point from the alpha limit set, which is the closest to the critical point from the right. And the number R is the first iteration when this interval covers the critical point C. Then, at first, we have these two inequalities. So yeah, we know that the numbers L and R are well defined because of these two inequalities. And it turns out that the points E minus and E plus are periodic. Moreover, the pre-image of alpha limit set of the point P has this form. So it is equal to set of all points whose trajectory never intersect this interval E minus E plus. And alpha limit set of a point P is completely invariant if and only if its pre-image does not contain point 0 and point 1. Okay. And yeah, so here we have the answer when this set is completely invariant. But what is interesting, the second statement is very useful to study the structure of alpha limit sets. Because, for example, we can say that any alpha limit set of expanding Lorenz map is either equal to the whole interval 0, 1 or a nowhere dense set. It is because the set of pre-images of critical point is dense. So if I have a proper alpha limit set, then it cannot contain any interval, because in any interval I have some pre-image of critical point. Okay, so from the second statement, it follows this corollary. And in fact, we can say much more about the structure of the alpha limit sets by studying these points E minus, E plus, and the numbers L and R. So, for example, if we denote by E of P the intersection of alpha limit set of P and open interval 0, 0, 1, it is because of some technical reasons we consider this set. We don't want to have endpoints in our alpha limit sets. Okay, so if we consider this set E of P, then if the numbers L and R are not equal, then the trajectories of these 2 points must be disjoint, and it is if and only if this set is a Cantor set. And if this set is a periodic orbit, then these 2 trajectories must be equal, and the points L and R also must be equal. And none of these implications can be reversed. We have appropriate examples. Okay, so let's move on. And now I will say something about dynamics on the alpha limit sets. So at first, note that the pair E of P and F restricted to this set forms a dynamical system. In particular, this set is closed. So it's closed, so it is compact, and we have a dynamical system defined on this set. And now denote by W plus the first R symbols from the kneading sequence of point 0. It should be 0 hat formally, but it is the same. And here should be 1 hat. Okay, so W plus is the first R symbols from the kneading sequence of point 0, and W minus is the first L points, first L symbols from the kneading sequence of point 1. And denote by F the set of all words of length R which are lexicographically less or equal to W plus, and all words of length L which are lexicographically greater or equal to W minus. Then the dynamical system. So the dynamics on this alpha limit set of the point P is topologically conjugated to this subshift, which is in fact the subshift of finite type. Okay, and I will show you some example. So let F be an expanding Lorenz map with this kneading invariant. So it is our Cantor example. In this case, E of G L is equal to alpha limit set of the point GL intersection of this alpha limit set with open interval 0, 1. And because this alpha limit set does not contain endpoint 0 and 1, it is just alpha limit set of point GL. Okay, and recall that the alpha limit set of this point was contained in the complement of the interior of the set W. So the union of these red intervals. And yeah, we proved that P1 and Q1 belong to the alpha limit set of the point GL. So P2 and Q2 also belong to this set, because we have a forward invariance. So in this case, the point E minus is equal to P2 and E plus is equal to Q2. Okay, so these 2 points are the 2 points from alpha limit set that are the closest to the critical point C from the left and from the right. And we can observe that the number L must be equal to 3 and the number R must be equal to 3. You can observe that, yeah, if we consider interval P2 C, it goes here to P3 1 after 1 iteration, then it goes here after second iteration, and after another iteration it covers the critical point C. And the same for the the second interval. So in this case, the words W minus is equal to 0, 0, 0, and the word W plus is equal to 1, 1, 1. Okay. And in fact, these two words completely describe the dynamics on this alpha limit set. Because now any trajectory in this alpha limit set can be described as an infinite path in the following graph. So for example, I can generate sequence 0, 1, 0, 1, 0, 1, 0, 1, and so on. And this sequence corresponds to periodic point GL. Or for example, I can have 0, 0, 0, 1, 0, 0, 1, 0, 0, 1. So it will be correspond to free periodic orbit. Okay, and each infinite sequence I can generate corresponds to some trajectory on this alpha limit set of the point GL. Okay, and I think it is all that I want to say. Here we have some references. And yeah, that's all. Thank you very much.
Are there any questions? Okay, if not, so let's everyone thank Łukasz. So
thank you.
And this is it. So see you all, I think, in a couple of weeks. Okay. See ya.
See you. Bye.
Bye-bye.